Now, I just want to let you know that for this session, right, I am not going to focus on qualitative analysis because I felt that I've done many sessions on qualitative analysis, but it's rarely, seldom focus on quantitative analysis. Usually only discussion of the lab report, the questions, then that's it. Okay, so today, this revision, we talk more about quantitative analysis, the titration, thermal decomposition, this kind of thing. Now, so what happened was yesterday, actually before yesterday, okay, I started a file long time ago. So yesterday I was just updating the summer 2023 paper. Try to write down the type of experiment for each paper 3. Now every paper 3 will have 3 questions, question 1, 2, and 3. So I just try to write down the type of reaction, type of experiments for question 1 and 2. Question 3 you already knew, definitely is going to be a qualitative analysis. Okay, so question 1 and 2. So just quickly, very fast, go through rate of reaction, enthalpy change, thermal decomposition, titration. Titration again, rate of reaction again, enthalpy change again, thermal decomposition again. Collect gas over water, okay, the water displacement experiment. Enthalpy change again, thermal decomposition again, titration again, titration, enthalpy change. This is already winter 2022, titration, thermal decomposition, enthalpy change, thermal decomposition, titration again. So, okay, so roughly just go through like a few sittings, you can see the trend. Always same type of reaction. So I have all of them here. Okay, not to say analyze, but kind of like to give you a briefing on what to expect in each type of experiment. First one, the most common one, titration. Now, titration, there are 2 types of titration, redox titration and also acid-base titration. Redox titration will always involve KMnO4, okay? Or iodide is oxidized to iodine, then you use starch. So these 2 types are redox titration. The rest are acid-base titration. So I have these first few pages to give you different colors of indicators. Okay, so the first one is starch. Okay, this is redox titration. So I put it here, usually in a redox titration involving iodine and iodide. So it will always be a reaction that they ask you to mix this, mix that, then you will see brown color solution that is formed. I remember that the last experiment, the one after the last practical after the trial exam, also we did this one. Okay, become brown. Then they ask you to do titration first until it becomes yellow. Then only you add starch. Then it turns blue-black. You continue your titration, you'll turn to colorless. Okay, so for starch, when they ask you to use starch in a titration, it is usually like this. Brown color, don't add starch first until yellow. Okay, add starch, then until it is colorless. But, okay, your title, the volume that you use from the burette must be from the very beginning. Okay, from here until the end. So the data that you record, okay, the initial volume, let's say you use and you fill up the whole burette until 0. So you should start from 0. Final will be until, okay, the endpoint colorless. So the one in the middle, that one that you stop, then you add starch, only you continue, and you don't have to record all that. Okay, only the beginning until the end, like any titration. Okay, now I maybe should shuffle later. Another redox titration will involve the use of KMnO4. Now KMnO4 is a purple solution. So initially, okay, you will add KMnO4 into a solution to oxidize something. So once KMnO4 drop into it, it always turn colorless first. Colorless, colorless, colorless. Then when everything inside here finish being oxidized, 1 drop of KMnO4 in excess will turn the solution into pale pink. Too much of KMnO4, okay, the purple solution or darker pink solution, this is over titrated. I think I should change this to, hold on, I want to change, yeah, the sequence was not okay, yeah. So now this is correct sequence. So add KMnO4, always turn colorless. This endpoint, this one over titrated. Okay. Now let's go to the one in the middle. There are a few very common indicators for acid-base titration. Methyl orange. Okay, methyl orange is yellow in alkaline solution. Red color in acidic solution, so the endpoint is orange. Yeah, very simple. You look at the name, methyl orange, so endpoint is orange. Bromophenol blue, okay, left hand side yellow, right hand side blue. I think it's again, the sequence was wrong. Okay, sorry. Okay, endpoint is green. Now, bromophenol blue is slightly more tricky. Sometimes in the exam, okay, in the exam paper, the instruction will tell you, okay, will tell you the color of endpoint. Okay, meaning the color of endpoint, if the question didn't tell you, it should be gray-green. But sometimes the question will tell you, oh, you should titrate until it is yellow. Then you will pass this stage to go to the light yellow. This is actually too yellow. Okay, past this green, okay, you will see yellow. So if the question tells you that you need to titrate until it is yellow, okay, then you follow instruction. Yeah, so I put it here. In case you are told what to do, what is the color of the endpoint, then you follow the instruction. If the question didn't tell you, then you should stop the titration at gray-green. Okay. Now, two more, okay, very common indicator in exam paper 3 now. Timol blue. Now, although Timol blue is called Timol blue, the color is not blue. Okay, Timol blue, can you see from the picture, it is actually orange. So again, just like methyl orange, okay, just like methyl orange, where's methyl orange? Endpoint is orange, right? So this Timol blue initially was orange, endpoint also titrate until it is orange. Okay, so your endpoint follow this color, just like methyl orange. Okay, timophthalene. Okay, timophthalene is colorless at the beginning. When you add into the solution, it is also colorless. Endpoint is pale blue. Over titrated will be dark blue. Okay, so I send you this. You look at the picture. The middle one is always the endpoint, except for starch. Starch, the endpoint must be colorless. The rest, okay, the middle one is the color of the endpoint, okay, including this KMnO4. Okay, so that would be the color of different indicators and their endpoints. Now, to remind you, for the table of results for titration, you need 2 tables. Okay, for rough titration, 1, accurate titration, another one. Now you can combine, okay, you're allowed to combine. If you want to combine, then this column will be, you have to add one more column here. Maybe I should just copy, hold on. B, combine table. Okay, rough titration. I believe that all of you prefer to be combined, don't have to draw so many lines. Last time they don't allow, but I realize that nowadays they do. So yeah, if you prefer it to be combined, then you combine. Then you probably have to be careful. This one must be labeled rough. Okay, if not, people will not know that it's rough titration. Okay, Now, if you already knew what to write, okay, for the headings, okay, if you are so used to initial period reading, final period reading, then the volume of the solution FA1, for example, FA1 use, then you stick to that one. Okay, if you are not, okay, you're like, I last minute still want to need some guidance, then you follow this one. I have a shorter one, initial volume, final volume, volume use. Don't forget the unit, okay? Unit, be consistent. You want to put slash, okay, then you put slash for everything. You want to put everything in bracket, then everything in bracket. Okay, remember, if you don't put unit here, last minute, let's say very last minute, in the exam, you make the table very close like this. Okay, you don't have space for the unit, then no choice. You have to write centimeter cube for every single reading. Okay, right, that would be, yeah, hold on. For titration. Now, to calculate the mean titer, now, mean titer, after you have done titrations, okay, choose two closest one. Cannot include rough, do not include rough. In the calculation of mean titer, okay, cannot. Only accurate titrations only, right? So these two, if you only do two, of course, you use these two. Find the sum, okay, add this reading and the other reading together, then divide by 2, that's the mean. Then you're going to use this mean titer in your calculation. Now, remember, I told you before, okay, if you think that you want to save time and you're very confident with your first titer, let's say you get 24.5, you think, yeah, it's 24.5, or even if it is not, it is very close, plus minus 0.1, plus minus 0.05, okay, you don't have to run the second one, you copy. Okay, so this is how you can save time for titration, because I believe that you've done so many times of titration, even from rough, let's say rough, you get 35 point something. Okay, because this one you ran very fast, you know that this is correct, then you don't have to run the second accurate titration, you just copy your results over. Okay, right. Now, even let's say if you are not confident, you ran the second time and you realize the second time you got 24.5, 24.00. I know it's not between 0.1, but you think that you want to save more time for the other two questions. The mean titer, you still take these two and find the average. Okay. I know you're going to lose mark, but it's better than, okay, you spend more time do third, fourth, fifth one, then you lose time on answering the question. Okay, even if you get like this, if you think that you are running out of time, you just use these two values to calculate, okay, the average. Right, now the next table is I have the calculation. I realized that the calculations questions are always very similar. They'll ask you to calculate the number of moles by using the mean titer. Then they ask you to calculate the number of moles of the other solution. You know, let's say you use FA1 to neutralize FA2. So the first one is you find the number of mole solution of this solution. Then after that, the other one is FA2, for example. Then you have to use the number of mole here to calculate the number of moles of the other solution. Now, the equation here, I say check equation. This check equation is always in the first paragraph of the question. Okay, find in the question. Let me see if I've opened. I didn't. Okay, let me just open one very quickly to show you where. Okay, for example, the first one is this titration. Okay, never mind, doesn't matter. Okay, you see, you always have the equation one. They'll always give you equation in the first paragraph, then you'll be able to find the ratio. Okay, whether it is a titration reaction or not, always there is an equation in the question. Okay, so find that equation so that you can calculate number of moles. Then after they ask you to calculate concentration, at the end, maybe molar mass of the something. Okay, now here is important, the dilution factor. Okay, I remember I taught you how to calculate the dilution factor. Okay, if you still have the notes, then you go back and refer, but this is very last minute already, right? I give you a shortcut, this formula. The dilution factor will be the volume of volumetric flask divided by the volume of pipette. They always in the instruction say, oh, pipette 25 centimeter cube of FA1, and then transfer it into a 250 volumetric flask. Then you top up the water until the mark, then you shake, right? So if the volume of volumetric flask is 250, volume of pipette is 25, so the factor will be 250 divided by 25. Okay, so last minute, you use this formula. Okay, now all this calculation must be 3 significant figures, the answer. Okay, except for the last one, if you are asked to calculate molar mass, molecular weight, relative atomic mass, okay, you follow the 1 decimal place in the periodic table. Okay, if not, everything 3 significant figures will be the safest. Now, if you struggle with significant figures, I don't know how, okay, I put some notes here so that you can also refer to, okay, if 1, that means this is 1, okay, 10 is still 1 significant figures because we only count the 1, we don't look at the number of 0. So you refer to this. If you're confused, you can ask me later, okay, like how to find significant figures. Now, I put the standard form also. Now, when we look at standard form, you don't care about the times 10 to the power of anything at the back. You look at the number in front only. In front of the multiply sign, okay, follow the rest. Okay, that will be number of significant figures. Now we come to the second type of experiment, water displacement, or collect the gas over water. This type. Okay, if you can remember, right, you fill up the basin, they always tell you at least 5 centimeter depth of water. Then you fill up the water in the very big measuring cylinder. Then, you turn it upside down. Okay, put it into the water, clamp with the retort stand. Okay, then you have your solution here. You add solid, you close the bung very quickly, collect gas. Okay, so this is the water displacement experiment. They will ask you to create a table. So this table follow the instruction. Okay, they'll tell you what to record down, but usually it is like this: the mass of container, the specimen tube, okay, containing the solid, then the mass of container with the solid, the mass of container of the residue after you add the solid into the conical flask, then the mass of the solid used, and important volume of gas collected. Now, how to read the volume of gas? Here, start with 0, right? Okay, so you have gas, okay, coming out, okay, forming. So push the water down, okay, push water down. So you are reading the volume of gas. So read like normal. So from 0, let's say this is 100, then the volume of gas will be 100 centimeter cube. Don't have to be oh, okay, I need to minus the water. No, okay, you're measuring the volume of gas. So how much gas occupied this? Then you just read from the measuring cylinder. I have calculation here. They'll ask you to find the number of moles of gas. Okay, divide by 24,000. This is volume, number of moles of gas at RTP. Cannot remember, there's a table of important values at the back of the question paper. Okay, right. So this one is actually quite simple. So far have not seen this sort of question asking you to do 2 sets to find the average. Normally only 1 time. I'm not sure whether they will change the question or not, but I feel it's very unlikely. They'll usually only ask you to do 1 time. You only repeat this one if, okay, no gas at all, or you think the gas that is produced too little. Okay, you can raise your hand, ask them to give you a refill of the chemicals, and then you can redo, provided you have time. Yeah? If not, you just move on. Right. I have the calculation here. So again, you can look through later. Now, the third type of experiment, okay, if you look at this picture, then you roughly know what is this. Okay, you have crucible, you have solid that can decompose upon heating, usually carbonate. Because you learn that carbonate can be decomposed. Usually group 2 carbonates will be decomposed when you heat them, usually metal carbonate. Okay. Group 2 or metals which can form +2 ions. Right? Okay. Right, I put here why group 2 and which can form, because you realize that usually in the question when they ask you to find the identity of the metal, they want a group 2 metal or any metal that can form a +2 cation. The equation given is usually MCO3. Okay, the formula of the carbonate is always MCO3. You know, carbonate ion is CO3 2 minus carbonate. Yeah? A bit small, sorry. Yeah, later I will just increase the size. Okay, you know that carbonate has a -2 charge. So the M, that ion, okay, to balance this -2 to form a 0 charge compound, that the M cation has +2 charge. Okay, that's why the identity is very important. Must be a cation that, must be a metal that can form a +2 cation. Okay, now I have the sample table results here again. Okay, they'll always want you to have the mass of crucible, empty crucible first. Whether or not to plus lead depends on question. Sometimes question will say, didn't tell you about the lead, then this one no lead. Okay, so up to the question. Then I put check whether lead is needed or not. Okay, now before 2022, I realized that they will always ask you to heat until you get a constant mass. That's how we ensure that decomposition is complete. But these recent 2 years, right, they don't ask you to repeat the heating anymore. Only one time heating. Let it cool down. Okay, they will always say, start question 3 while waiting for the crucible to cool. Okay, then after cooling down, come back, they'll only say, okay, now reweigh the whole thing to get the final mass. That's it. Okay, no more heating. So again, you check if the questions ask you to do more than one heating or not. If not, right, you don't need this 1 and 2. You only need 1 reading. Okay. Now always 1, 2, 3, 4, 5, 6. I realize 6. They'll always need 6 values. With lead, empty one. Okay, whether we lead or not depend on question. Second, you add solid. Okay, third one, okay, after heating, then these 3 based on calculation. Now from the trial exam, I realized that this calculation apparently is quite difficult. But the mass of FA1 used is the second one. I put A, B, C, yeah. Let's say this is C. Okay, mass of FA1 used will be B minus A. Okay, before heating, okay, you have empty crucible but S plus FA1, right? So minus the crucible, you get the mass of FA1 used. Now, mass of residue will be C minus A. After heating, okay, what is left is residue. So now you have crucible with residue. So minus the mass of crucible, you get the mass of residue. Now, mass loss is something that's lost, no longer there. Okay, no longer there. So it is B minus C. I hope that you look at how to calculate this one before you enter the lab in case this one come out, right? I remember a lot of people got confused between the mass of residue and the mass loss. So loss means the CO2 that is lost no longer there. So don't get confused with these two. These two wrong, then you're going to lose like 2 marks, I think. because you are going to use it for calculation also. And also, they are going to calculate and see your calculation, if your calculation is correct for the whole table. Okay, right, that would be third one. Now, fourth one, enthalpy change. The one that you use polystyrene cup. Now, this one is longer because I have few types, I think 3 types of enthalpy change experiment. Now, first type is a very simple one. You add solution, you add solid into the cup, you stir, you get the final temperature. Okay, or the maximum temperature that is reached. So far, I only saw like in past year papers maybe twice that the temperature will reduce. So it depends. If the question say maximum temperature, that means temperature will increase. If they say minimum, that means that reaction is endothermic, then the temperature will decrease. Okay. Right. Of course, before you start adding the 2 reactants together, you need to record initial temperature. So this is the simplest one. So I have the sample table type number 1. Okay. Then sample table type number 2 will be the one that, at the beginning, remember, for the first 2 minutes, you just stir. Every 30 seconds, you record down the temperature. Okay, you realize that usually it is quite constant. Then at 2.5 minutes, they say, add zinc powder. Okay, so you add zinc powder. So here you shouldn't record any temperature, okay, because you are doing it alone, right? You can only add solid at that dot, okay, on dot 30 seconds. Okay, you add. So you're waiting for the next 30 seconds, you start recording more temperature. Of course, the table will be longer than this one. Usually you have to record until 9 minutes, I think 8 or 9. So of course, this one is very long. Okay, you have more. Okay. Sorry. Now, here note temperature must have at least one end with 0.0 or at least one ends with 0.5. So you have everything ends with 0.0. Please, at the end, before you start your calculation, change 1 to 0.5. Okay, I will suggest you to change the graph here, right? Change somewhere between here. Okay, one of these, because this one will not affect your graph. Okay, or you can just plot the graph first, then you change, because I want you to change the points between the 2 lines, because these 2 are going to affect your line of best fit. So change those that will not affect your line of best fit. Okay. Now let's go to the graph. Yeah. So type 2 experiment will lead you to a graph that looks like this, the S-shaped graph. Okay, S-shaped or reverse S-shaped graph. This one is to help us find the delta T. So you plot everything. Okay, do not draw any line to join all the dots together. No. Okay, we only need 3 lines. 1, the beginning. Okay, 0 until 2.5, because that is before you have added anything. Okay, you haven't added, let's say, copper sulfate solution and zinc, right? You haven't added zinc yet. So before you draw one line of best fit. Okay, in this case, all straight lines only. Straight lines. Second straight lines after maximum temperature has reached. Okay, draw one line of best fit. Go through most of the points. Okay, remember, points above and below must be balanced. That's your line of best fit. Okay. Third one, you extrapolate these 2 lines until at 2.5 minutes. Okay, sorry, this graph is at 1.5, but your experiment is 2.5. Extrapolate until 2.5 here, then you draw one line, go up. Okay, intercept both these straight lines that you have drawn. That will help you to get the delta T. Yeah, let's say if you have one line here, 2.5 minutes, your experiment was 2.5. Then your delta T will be from this, okay, this intercept until the other intercept on top. your delta t. You're going to use this delta t in your calculation later. Okay, calculation. Right, I'll go to calculation later. So if your experiment is different, very unique one, start from higher temperature, then endothermic reaction, so you go down. Also the same thing, okay, before one line, okay, after minimum, one more line, and then at the time you add the solid, a vertical line, that will be to find your delta T. So this is type 2. See, type 1, no graph. Type 2, the S-shaped graph. Okay, to find delta T, then you use the delta T for calculation. Now, please follow the instruction very clearly. Normally, they will say you need to reserve extra 5 degrees Celsius above your maximum temperature. Okay, because see, this line might go down like this. So you will need the 5 degrees Celsius above the maximum temperature to read the delta T. Okay. So I have notes here. Please do not start this graph from 0 for 5 axis, or y-axis, sorry. Because if you start from 0 here, I'm sorry, your graph cannot occupy more than half of the graph space given. Then you will lose 1 mark. Okay, so anything that involves temperature, the graph do not start with 0 on the y-axis. Okay, no need to start with 0 here. Can start with the initial temperature, okay, or any temperature that you think your graph will occupy most of the space. But third line, okay, third line is this one, okay, to calculate the delta T. Okay, so before calculation, let's go to tab 3. Yeah, I told you many tabs, right? That's why I spend longer time on this enthalpy change. Now, tab 3 will be you add acid, okay, or the alkaline portion by portion into the other solution. Let's say you start with solution, acid solution in the cup. Okay, first add 5. Sorry, before adding, you record initial temperature. Second time, they say, oh, add 5 sodium hydroxide, 5 centimeter cube sodium hydroxide. So you add, get the maximum temperature again. Then add another 5 centimeter cube portion, okay? And then so you record down the temperature one by one, until total is 40. That means you have added 8 times of sodium hydroxide. Every time 5, right? Plus 5, 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 plus 5. So this is just total. I copied this one from the question. I realized that usually when they want you to add portion by portion, they give you the table of results and you just fill in only the temperature. So if they don't give you, I don't know how many times they will give in exam paper. If they don't, remember the type of graph is at the type of table is like this. Okay, add 5. Okay, second time add 5, total is 10. So 5, 10, 15. Okay, record temperature, everything. You will plot a graph. So tab 2 and tab 3. Okay, you'll be asked to plot graph. Now, tab 3, the portion by portion one, the graph will look like this. They want you to draw one line from the beginning until maximum temperature. Second line from maximum temperature until the last one. Then you find the intercept. The intercept will tell you the exact volume of NaOH needed to neutralize the acidic solution. Okay, now see this one, the graph, they always say draw lines of best fit. I want to tell you that line of best fit means the type of line that can best fit the plots, the dots. So if the dots looks like this, you know that it cannot be a straight line. It looks more like a curve. Then please draw a curve. Okay, you see a curve just nicely fit into the dots, right? Okay, but if you insist to draw a straight line, you manage to get one line where you get equal number of dots above and below is also acceptable. Okay, but if cannot, please don't force you draw a curve. All right. So could be the curve could be on the left hand side also. I just give you an example only. As long as you see the dots, you think that it should be a curve, then you draw a curve. So line of best fit doesn't mean that it must be a straight line. It can be a curve, right? Then delta T again is obtained from the graph. So from the very beginning, when you have 0 sodium hydroxide, until the volume of the exact volume of sodium hydroxide needed for neutralization, you find the delta T. Then again, you're going to use this delta T for calculation. Now, whether, okay, type 1, type 2, or type 3, you will be asked to calculate delta H. Why? Because it's enthalpy change reaction, right? So how to calculate the heat? First, the heat before at delta H. Use Q equals to MC delta T. Now remember the M, although we have learned that M is actually mass of something, right? But it's actually the mass of water, and we always assume that the density of water is 1 gram per centimeter cube. So in this case, the mass of water become the volume of the water because density is 1, right? That means mass and volume will be equal. So use the volume of the solution. So if we add, you see, in this case, let's say you start with 25 centimeter cube of acid. After everything, okay, after you added everything, it will be 25 plus 40 sodium hydroxide. Total volume. I should put total volume of solution. Yeah, sorry, this is not accurate. Acid plus alkaline. Okay, the total. Right, now delta T here, please use the one that you obtain from graph. Okay, from graph. This one no graph, then you use the temperature change. This is the delta T. No graph, you use the table. There's graph, always use delta T from the graph. Okay, don't use the one in table. I use the maximum minus the minimum. No, no, no. When there's a graph, use delta T from the graph. Okay, right. Now, of course, not only the Q. Okay, Q is not enough. They want you to find enthalpy change of neutralization. Okay, for neutralization. Oh wait, sometimes it's not enthalpy change of neutralization. Okay, now let me put here. If enthalpy change of neutralization, okay, N is the number of moles of water. Oh. Let me try to save some space. Okay, can see So delta H will be positive or negative Q over N. Remember, this is only finding the amount of heat being produced from the experiment, not delta H. Delta H is kilojoule per mole. Q is only kilojoule. The unit is only kilojoule. Here we want to find kilojoule per mole. So you need a per mole, right? Per mole of what? For neutralization, okay, the mole is the number of mole water formed. So in between this Q and delta H, they'll ask you to find the number of moles of HCl, the number of moles of NaOH. They react, how many moles of water that is formed. You can get from equation, yeah. Then you use that number of mole, okay, to find your delta H. If temperature is increasing, okay, this reaction is exothermic. Please add negative in front of this delta H. If it is endothermic, then you use positive. Okay, positive or negative. Okay. Just try to save space. Okay. The last type of experiment, the rate of reaction. I don't have a picture here. The rate of reaction is normally the one that you have the insert, the printed insert in your paper, which looks like this. Hold on. I think I have that insert in this. Okay. You have used it before in the lab. It looks like this. Okay. We laminated and give it to you, right? Then you're supposed to place your beaker on top. Then you add something, you add don't know which solution together. Then they will form a they'll form solid. Okay. Or you add starch indicator, the solution will slowly turn blue-black to then you're unable to see this shrinking anymore. Okay, from the conical flask, from the top of conical flask, then you stop the timing. Yeah, this is the rate of reaction experiment. So usually they will give you the experiment number 1, number 2, number 3. Then they'll tell you that, oh, inside your table, you're supposed to include the volume of FA1, volume of FA2, volume of water. Okay, then you have reaction time, then you have to calculate the rate of reaction, usually 1000 over the reaction time. Then after you follow the instruction, everything, you realize that they will always ask you to suggest, okay, more experiment, because this time they probably want you to investigate the rate of reaction, the effect on the rate of reaction, okay, of the other concentration, the concentration of the other solution. Then you must be able to suggest. So that one is, if person asks you to do more experiment, you find out the range of the independent variable, this one, okay, according to the range. But I believe that you already know how to do because you have done this before. The one that you want to investigate the concentration, the effect of the concentration, you change the volume. Okay, then the rest you have to be constant. Okay, and another thing that you need to change will be the volume of water. You want the total volume to be the same for every experiment. Okay, reaction time, please record to the nearest second. That means no decimal place. What does it mean by no decimal place? Okay, it means 1 second. 1, no decimal place. Okay, 1.0. Okay, 1.0 means it has a decimal place. When I see point, behind that point has something, that means there is decimal place. Okay, so no decimal place means only whole number. Okay, only whole number, no point something, even at the back is 0.0, also not acceptable. Okay, so please remember only whole numbers. And the rate will be 1000 divided by this reaction time. Now, usually rate of reaction they will ask you to draw a graph. Okay, after analyzing, okay, most of the graph, 99% of the time, the graph is the straight line. Okay, so far, I only seen like one time it is a curve. If it is a curve, it is very obvious. The dots, okay, let me draw. The dots will actually be very obvious that you can't draw a straight line. Okay, can you draw a straight line using this one? No matter how you draw, okay, it's very difficult for you to get the balanced number of points above and below. So this is a curve. Okay, usually it will be a straight line, 99%, right? Okay, so if you do not think that much, you always draw a straight line. Now, if you can, please make the straight line to go through the origin. Okay, if you can. If not, then you don't have to force it. Okay, but most of the time they design the experiment for you to be able to draw a line that can go through the origin, or at least close to the origin. Okay, but it's okay if you think that cannot, then let it be, but the way you answer the question will be different. After you plotted the graph, you always ask a question. Okay, if this reaction, the rate of reaction is directly proportional to the concentration of the solution used or not. See, on the x-axis will always be the volume of a solution. I just put an example here, Fa2. Okay, it could be Fa1, could be Fa4, whatever solution. Okay, they will ask you, is this rate of reaction, is the rate of this reaction directly proportional to the concentration of this solution used? So if your graph is a straight line, must be a straight line, a curve don't count. A straight line that goes through the origin, like this exactly, then you say yes, the rate of reaction is directly proportional to the concentration of Fa2. If your graph is a curve, okay, if a curve, then okay, no, the answer is no. The rate of the reaction is not directly proportional to the concentration of Fa2. Yeah, if a curve or a line which doesn't go through the origin. So there's only one condition that it can be direct proportional to the concentration. It must be a straight line that goes through the origin. Only one condition. Other than this, or no, not directly proportional. Okay, always ask this question. I realized many times. Now, also recently, there's another type of question that's very popular. The depth of the solution. They'll ask you, okay, what's the difference? If I use beaker, okay, is all this one, all the experiment, I use a Petri dish. Okay, now I decided to change it to a beaker. So the solution, the reaction time will be longer or shorter. Okay, if you're using something deeper, okay, something has bigger depth like this, then the time will be shorter. You use a wider one, so very shallow solution, right? Then the time will be longer. Okay, let me tell you why. It is because I need whole space. Okay. How do you see the solution? Okay, covered this writing, and you won't be able to read this writing anymore, right? It's because let's say I have a reaction that is producing sulfur. You know, you have seen this type of reaction before. Two types. One is the solution will turn cloudy. Okay, become white, right? Because of white solid form. Okay, so more and more white solid form, then at the end cover the writing. That was sulfur. Okay, thiosulfate will always react with acid to form sulfur. Of course, this is not balanced. I just want to tell you that sulfur is formed. So if you use beaker, you put it on top of the printed insert, you have words below, right? So when you have more and more sulfur being produced, so all this sulfur, okay, one layer, imagine you have a lot of, the solution is deep. So all these sulfur molecules, molecules or atoms, okay, they stack on each other. Okay, they stack and stack and stack on each other. So when you look from the top, right, they are covering the writing because it becomes more and more packed. Okay, more and more solid form. Then it will actually hinder you from seeing the writing. So imagine now, I use Petri dish now. It's so shallow. So yes, I have sulfur form, but you see, you have less layers of sour being stacked on each other, on one another. So you need more and more and more sulfur being formed. There only you have enough sulfur to cover the writing on the paper. So that is why deeper one, okay, you have deeper solution. So it will take shorter time to produce enough sulfur, enough solid, okay, to cover the writing. This one shallow, so you need longer time. You need more sulfur solid to cover the writing. Okay, same goes to if you are using iodine and starch. So this iodine and starch will form blue-black solution, right? So you need more iodine to be formed for Petri dish. You need more iodine to be formed so that they will react with starch, okay, to turn the solution blue-black enough to cover the writing. Okay, but this one, because the solution is deep, you need less iodine. Okay, less blue-black because they all stack on each other. You need less, then you have more layers to cover the writing. This one you have less, so you need more iodine. So this is another very popular question for these few years. Okay, the depth of the solution. So next is I'm going to talk about some of the common things that they might ask, or you might want to know in the experiment. The part 2 will be accuracy, precision, modification. So for the type of reaction, okay, I just want to like give you more remarks here. Like if you do titration, you must get 2 titers within 0.1. Okay. The water displacement, the one you cannot guess over the water one. The average of 3, I think this is not applicable anymore. This is not older ones. I'm going to delete. Yeah. Thermal decomposition. Okay, thermal decomposition. Usually you have to reheat, reweight until you get constant mass. Even if they don't, in the question they will ask you, how will you change the method of this experiment so that you can make sure that the decomposition is complete? Then your answer will be reheat, reweigh until constant mass. Okay. Now for enthalpy change rate of reaction, normally you have to look at the graph and see whether there is any anomalous points or not. If there is, okay, you say, oh, I need to actually repeat the point that is anomalous in the graph. The next one will be the apparatus, okay, the usual apparatus that you use for measuring. Okay, so here I have the precision to tell you how many decimal places in the reading that you should have. Burette reading must be 2 decimal places. Pipette 1. Thermometer, okay, 1. Also 1 decimal places. 1 decimal place. Okay, usually ends with 0.0 or 0.5. Then weighing balance, we always provide you with the 2 decimal places weighing balance. So your reading should always have 2 decimal places. Now the error and uncertainty in a single reading, single burette reading, that means I read only one time. What's the error? 0.05. Pipette, usually this one you'll be given in the question because sometimes they ask you to use 25, sometimes they ask you to use 10, right? So they will give you that one. Thermometer will be 0.5. So if you really cannot remember all this, you go and look at the burette, the pipette, the thermometer, the weighing balance, right? What's the smallest division? So burette one, you just zoom in, the smallest one, right, will be 0.1. So 0.1 divide by 2, always the smallest division divide by 2, that will be your error for a single reading. So the smallest one is 0.05, sorry, 0.1. So divide by 2, 0.05. So that will be the error in one reading. Thermometer, the smallest one is 1 degree Celsius. So divide by 2 will be 0.5. Weighing balance, I know you can't see the smallest division, but okay, 2 decimal places, for example, okay, when it is 0, so it will be 0.00 gram, right? Okay, so you see smallest division will be this one, 0.01. The smallest mass that you can measure is 0.01. So 0.01 can be the error, or you want to divide by 2, be consistent, divide by 2 like the rest, the error will be 0.005 gram. Okay, they can accept any of these, so it's up to you. I don't know which one is easier for you, right? Okay, you choose. Oh yeah, I have one more. Stopwatch. Stopwatch, no decimal place. Okay, they don't accept decimal place. That's why, you know, in the rate of reaction experiment, you have to record the nearest second. And if they want you to calculate the uncertainty in the reaction time that you have recorded, they will give you the uncertainty. This is a very rare question also. I've seen only few times, maybe the most twice. They give you the uncertainty so that you can calculate, okay, the uncertainty or the percentage error in the time recorded. Okay, then I have a formula here for percentage error. This one is hard to put, because it can be volume. Okay, volume, temperature, the mass, and this is time. Okay? So it depends on which one they want you to calculate.